Okay. Hello, can you hear me? Can you hear me? So, this is Saturday night. I'd like to start a tutorial live for Houdini for this week. This is the series called Houdini Algorithmic Live, and today is 104th episode. The topic is about to implement the paper called Developability of Triangle Meshes to create a developable surface from input mesh geometry. Okay? And so today is more like a paper implementation day for me, and this is one of the paper that I was into for a long time. I wasn't really ready to do the implementation because of the lack of geometrical knowledge. But now I have tried, and it seems I have made it just the essential part of the paper, but it seems to work as it should be. So I would like to share what I have done so far. What I have implemented from the paper is mainly two things. One is to evaluate the energy in order to create a developable surface. There are two major energy explained in this paper, and I'm just going to explain one of the energy implementation on Houdini. And then another stuff that I have implemented is to is the optimization in order to find out the best time step to do the optimization, okay, using a linear search. But I didn't really look into those different types of linear search. I just implemented my dirty version of my linear search. So I don't think my optimization stuff is that optimized well, but still works for any resolutions of meshes, so I'll just tell you that. And if you are really into this kind of stuff, optimization stuff, then you could look into different types of linear search or optimization method to implement for yourself. Okay. And I am also skipping a lot of like tips explained in the paper in order to make the best version of developable surface, in order to like avoid like a flat surface or double surface stick together or pointy meshes and so on. So yeah, I'm going to skip all those stuff. But if you are into it, then again, after implementing this essential part of the paper, I think you could just add several conditions to make it more developable or more clean mesh. Okay. Well, I just thought putting the essential part is the most important things in this paper, so that's what I'm gonna show you how to do that. Okay. So you could go to this web page on the Keenan Crane website. The project is called Developability of Triangle Meshes, which is the paper from SIGGRAPH 2018. You can download the paper in PDF from here. There's a video also as well explaining the the possibility and the basic method how you're going to calculate the energy. And there's also a code which you can download to test out for yourself in C++ in GitHub, which I couldn't build myself on a Mac OS environment, so I couldn't really try it out myself. But it will be interesting to see this as well, maybe later. Since it's using Levi GL library for C++, which is a geometrical processing library, which I never used myself. So the code explained in this in this repository is a bit too much for me. Maybe I should really look into it in order to create like several conditions and explain in the paper. But for today, we're just looking at the paper to try to implement what it says as an essential stuff. All right. So let's look into this, and this is kind of a result that we are going to get today. First, you input the mesh any kind of resolution in any kind of resolutions, and I am going to use a solver to implement the one explained in the paper. And inside the solver you have a bunch of node. This is where you are calculating the energy in order to estimate which part should be developabilize in order to make it developable. So this is where you calculate the energy, and this is where you are doing the optimization using the dirty linear search implementation that I did. Okay. I'm gonna explain it later. And using the solver you can see the results step by step on each frame, and this is what you're going to get out of the result of implementing the paper. And I think it would work in any kind of mesh. You could also try with this kind of rubber toy geometry as well. It could still work, and the speed is pretty decent, I think, because we're using Vex most of the time, Vex to do the parallel calculations for each vertices, and you see these ridge edges become obvious to create a developable surface. Well, there are some stuff which might be hard to use it as a real developable surface, so there might be other way to solve this one, maybe explained in paper, but this is just the result of the essential implementation of the paper. For example, if you look at this part, you see that the surface becomes flat, so there are some explanation in the paper in order to avoid this kind of conditions. But besides that, it looks pretty nice in terms of the result. So shall we do this? I mean, after implementing the basic stuff, you could just go with yourself to make it improved. Right? So going back to the paper, we need to know what kind of problem we have out of the base mesh. Okay. In order to solve the problem, we need to know what the problem is, and the problem here is how we can make the surface developable. Developable means a surface that you can unfold to make it a flat surface, okay, without any distortion. So in order to do that, the surface has to have some conditions, and that is explained right here. If you look at each vertex, and if you look at the neighbor points on the specific vertex, the normal map, these points are the normal points, the direction of the normal plotted on the sphere. And if you plot all the normal direction for each neighbor points on top of the sphere, if it is developable the overall shape of these normal points become straight line, or the area with the zero area, or just a point if it's all flat. So and if there is like curvy surface, if it's a curvy surface, and if it's not developable, then you will have some kind of area around here. If I light it, if I draw it. Okay, sorry. I have just okay, so if the surface is not developable, then what you get is, okay, how do I draw this thing? Okay, it's not working. Forget it. You get some kind of area, you get some kind of polygon on top of the sphere, which have some area more than 0. So what you want to get is the condition like this for a normal distribution, which is called as Gauss map. And in order to do that, it explains 2 ways to calculate the energy in order to achieve this result. Either this hinge-like condition or a flat surface. And you could, going into the chapter 4, it explains exactly how you could calculate the energy. So if you are really curious about the detail of the conditions, how it should be made, you should read the chapter from chapter 1 to chapter 3. And the chapter 4 explains the detailed explanation how you could calculate those energy in order to solve, or in order to make the mesh looks like these conditions. Energy means some kind of a force in order to move the point to a best position. Okay, so it's more like a direction of the point to move with some kind of amount. Okay, and after you have got this direction, in order to move the point, you also need to estimate how much you should move to that direction per step, and that is decided when you do the optimization part using a linear search. So first of all, what you need to do is to estimate the direction and basic amount in which direction you should move the point to get this developable condition. Okay, and the chapter 4 is explaining how you could calculate this energy, and there it explains that there is 2 ways to calculate the energy. One is to use the combinatorial width by simply looking at each point and pick a pair of meshes which sticks to this point. For example, if you are looking at this point, pick this mesh part as one of the part, and pick this mesh part as another part, and calculate the conditions between 2 meshes in order to check if this is doable for a hinge condition. And do the same for all the other pairs, like this mesh and all the other mesh with these mesh pairs and these mesh pairs, and so on. So you gotta look for all the pairs which is available on top of this each point. Now, as you can imagine, the calculation cost is pretty high for that energy, because you have to find all the possible pairs out of each point. So that's not ideal for fast optimization, for fast calculations, so we're going to skip that. Instead, what we are going to look at is the second energy, which is a covariance energy. Okay, this is to estimate. This is to give a condition. This is the how do I explain this? For example, if you have a hinge like that, where you have a folding angle, folding axis like that, there is a specific conditions available with this kind of mesh, which is first of all getting the normal direction of each face which belongs to this point. So the normal is something like that. Okay. So normal for each faces, get the normal for each faces, and if the hinge is developable, if this mesh is developable, that means all the normal are on top of a specific plane. So I'm drawing really bad, but if you take this plane out and if you take these normals out, actually all the normals are on top of the same plane. Consider this is x and y, meaning the normal direction is made of ax plus by. A or b could be any value, but so meaning there are no z axis value used in this normal direction. That's what I mean by all the normal direction is inside the same plane. So that's when you get this. That's when you know that this mesh that you got from this point is developable, meaning foldable, unfoldable. Okay, you could say the same for the flat mesh. All in terms of the flat mesh, all the normals are facing upward, like that. So any plane could fit if the one of the plane axis is in the same direction. Okay, so that's how you can estimate that the mesh is developable, and you could check the fitness of each normal direction on a plane, and if it fits well, then the energy is equal to 0, meaning you don't have to optimize that. If the value is really big, then that means if there is an offset between each normals, if the normal is not on the same plane, and if the angle is really big, then that means there's a lot to fix, and the energy becomes really big in order to fix that. So that's how it works for this covariance energy, and it explains how you could exactly calculate that energy. Okay, so this is where it explains the conditions. So what you need to do is to first of all calculate the dot product between the u is the the unit normal of the plane, which I am explaining, the fit plane. Okay, this fit plane, this is u. Okay, and the normal of the surface each face. So if it is perpendicular, meaning the dot product will become 0, so the energy will become also 0. Okay, So that's where you want, that's the goal in order to achieve the developable surface. Okay, and you are also multiplying with the angle of each face in order to use the angle as a weight, because when you are using mesh, there is a possibility that one of the face has a really big angle, so you are using that angle to kind of coordinate the weights. Like calculating the average or something like that. Okay. And finally, you are going to look for the minimum. When the result of this value becomes minimum, then that's the goal for the covariance energy. And in order to get that energy, it explains here the energy, how do I call this? Forgot how you call this in Greek word. This word can also be expressed as the smallest eigenvalue of 3×3 normal covariance matrix of this. So A is the matrix, 3×3 matrix, and you can calculate this matrix by calculating the outer product of the face normal multiplied by the angle for each face and add it all together. Then that becomes the 3×3 matrix, and by getting the eigenvalue of this matrix, you'll be able to get around 3 directions with 3 eigenvectors with 3 eigenvalues in maximum, and the minimum of these eigenvalue is the most fit direction of the fit plane. So that's the one you want to get, and that's the one, the associated eigenvector is the one in order for you to calculate the actual energy in order to optimize the gradient, optimize the developability. Well, I'm not sure if you get that out of what I explained, but that's the whole goal. So what we need to do is to calculate this stuff, okay, and estimate the eigenvalue and the eigenvector from 3×3 matrix, and use that to calculate the actual energy as a gradient in order to move the point. And you could get that equations going into the chapter B appendix, going to be 1, B3. So B1 and B3, you will see those equations in order to calculate the actual gradient, the direction, in order to move the point for the best position for each step. Okay, so that's the goal. I don't know if you got it. So first thing first, what we need to do is to calculate the scalar value for the energy, and you could do that by going back to the chapter 4, and where was it? Chapter 4 and this one. So this is the first goal, right? Oh yeah, thanks for the comment. This is called lambda. Okay, so shall we do this? Enough for the explanation. We should start calculating this stuff, shall we? So let me bring up the geometry node, also save the 1 to the folder for today. Okie dokie. Okay, so we could test out with different types of geometry. Let's go with the simple stuff first, shall we? Something like, although I think it is best to do it with a regular shape, so maybe we'll just use the test geometry after all, like test pig, big head. And since we are going to solve the problem on top of the triangle meshes, like it says in the paper, this is the process for the triangle meshes. So we cannot use this for the quad mesh, so let's make it triangle mesh first. We can either do it by divide or remesh. I think we want to do remesh first, because this will create kind of a uniform triangle shape, which is easier for geometrical processing rather than this irregular triangle shapes, like the size is different, there are some directions and so on. So the condition for out of this divide node in terms of the geometrical processing is not that good, I think. So let's go with remesh first and make the target size small enough for processing, something like that. Okay, now the texture is messed up, so let's just delete the material out of this geometry. I'm gonna use the attribute delete to delete the material information, maybe the UV as well. Alright. Okay, so let's go with this. Now what we wanna do is to calculate the eigenvalue and eigenvector for each point out of this matrix that's explained in chapter 4, which is going to be the energy for the developable surface. So let's see how we could do that. Okay, I'm gonna put this on the side and see how we could get these information. Alright, well, I think this calculation is pretty simple to do, so let's see. First of all, we need the normal direction of the face, so let's create that using the normal node. Thank you all for coming and for the comments. Let me know if I'm doing something weird or something wrong. I mean, I'm not a professional like engineer or a mathematician or so anything. I'm just doing this as a hobby, so I know I think I'm doing something wrong. So so if you find it anything weird or wrong, then just tell me. I'm glad to hear that. Okay, so first I'm going to calculate the normal for each faces using the normal node with the primitive option on, so that you can get the normal direction for each face, which stands for this Nijk. Ijk stands for the vertex at I. So if we are looking at the point I, then this will be J, this will be K for the first iterations, and this will be I, this will be J, this will be K for the second iterations for each face that belongs to this point. So we have, in this case, 1, 2, 3, 4, 5, 6, 7. 7 faces, meaning you have 7 iterations for this equation. So you are, since we have sigma here, we are adding these value 7 times for this points. Okay, so which means it makes sense to do the calculation per points. Right? Let's do that. Point wrangle. And how do we name this? Calculate the energy. or how do I call it? Well, yeah, I'll just call calculate energy. Okay, so first thing first, we want to get neighbor primitives for each point. So for this points, you can get the neighbor primitives, the primitive that belongs to the point by using a function call point prims. Alright, so in case of this point, you get 7 primitives. Alright, then let's loop this primitive to do this calculation here. Okay, and as a result, what you want to get is the 3x3 matrix. Okay, so in each iterations, you're going to get some kind of 3x3 matrix value and add it to a global value. So let's create the global variable for 3x3 matrix, call A, make it empty for now. 3x3, so you have 9 zeros as an initial value. Okay, now let's go step by step. First of all, I would like to get this normal direction for the face. So get the face number like that, and then get the direction of the normal using prim function at this primitive. Right now, in order to do this calculation, the normal vector multiplied by normal transpose of normal vector value, which means normally in the paper the vector means the vertical looks like this. So let's call this n, and n transpose means you have a, b, c. Okay, and by multiplying these two values, you get a multiplied by a, b, a c, b, a b, b, b c, a c, b c, and c. Okay, so this will become 3x3 matrix. And you could actually calculate this using a function in Houdini called outer product, which is this one. There you go. And if you look at the explanations, yeah, same as this one. You are multiplying U and V transpose to calculate this matrix. Okay, so that's the function we want to use here in order to get this value. So going back to the vex, let's call it matrix 3 temporal A is equal to outer product between a norm, and actually there are no way to transpose the vector in vex, so you can just say norm again and then you'll get the value. It looks a bit weird, but it works like that. Okay, then what you need next is this angle value here. So for this face, the angle we are mentioning about is this angle right here. It corresponds to this I value, the I point position. So if this is J, if this is K, what we want to get is the J, I, K theta. Same for all the other meshes. So in order to do that, we need to know the point position for the center and point position for the neighbor points from this primitive. So let's get that. First we get the corresponding points from this primitive using prim points. Then since this is always a triangle mesh, we know that we have 3 points inside this array at all time, and we know that the current point number on this point wrangle also exists inside this point list. So let's remove that value out of this PTS. Then we are left out with 2 points, either this one or this one. Okay, now we have point for each point on the neighbor and the center. We could start calculating the angle. Let's get the points on these neighbors. One is PTJ, which is the first point from this list. PTK, which is the second point from the list. Then we need to know the actual position for that point, so we get the point attribute from each point. And we do know the center point, which is equal to at P. Now we have 3 points. It's time to calculate the angle. Now, in order to calculate the angle can be retrieved by arc cosine of a vector AC dot AB, and you also want to normalize this. How do I normalize this? Like that. And this is, or maybe you could say divided by the length of AC multiplied by length of AB, like that. So this is the angle for this theta. So let's do that. Float angle for theta is equal to a cosine, arc cosine of the dot product between the position j minus position I, which is the vector from I to j. And we also want to normalize this. And normalized of position k minus position I. A lot of parentheses. Now this should be the angle for each faces. Belongs to this I. Okay. Now that we have 2 values, the theta, ijk, and these outer products, 3x3 matrix products, we can now add these value to a global A inside a loop by TA multiplying by theta. Like that. Okay, and as a result, you should be able to get the 3x3 matrix at this point. Let's check. Okay, for each point. So going into the geometry spreadsheet, looking at the point, and there you go, you are having a 3x3 matrix. Okay. Now, from this matrix, you need to get the eigenvalue in order to estimate the energy on top of that point. Also the eigenvector for the gradient. So in order to do that, we can use another function on Vex to estimate the eigenvalue using SPD decomp, this one. Okay, well, SPD decomposition will decompose the 3x3 matrix into U, S, and V. And most of the time you only use U and S, and U will become the list of eigenvectors and S will be the value for the eigenvalues. Okay, combining those two values, you'll be able to get those two different values. This SVD decomp not always gives you the exact precise information. So in order for you to get the precise information, the best bet is to make this float value into a double value. In order to do that, you go to the bindings of this Vex triangle, then change the Vex precision to 64-bit, then the float becomes double precision. I think that's necessary, and I think that was also explained in the paper that you do need to use the double precisions for this calculation. Okay, so after you have got this matrix 3A, it's time to actually calculate the SVD decomposition, and this is how you use it. Let's bring this back here. So the first input is the matrix, and then you get the output parameters like U, S, and V. Right, so first of all, let's create the empty variable for U and V, which is a matrix 3x3 matrix. And the output S is the vector, so name it as S and make it as an empty variable. Now it's time to use the SPD decomp. The matrix you're going to decompose is the A, and the output is U, S, and V. Okay. After this, you'll be able to this function will insert some value to U, S, and V, and let's see how it looks like. So for U, that is 3x3 matrix. For V, that is also 3x3 matrix, and S, that is a vector. And if you look at it, first of all, if you look at the S value, this is actually the eigenvalue, and as explained in the paper, what you want to look for is the minimum of this eigenvalue somewhere. Let that here. The lambda I can also be expressed as the smallest eigenvalue of the 3x3 normal covariance matrix. So you want to get the smallest one. Meaning, in this case, the third one is always the smallest. If you compare with the left-hand side, S0, S1, you see that the S2 is always the smallest compared to the ones on the left side. Okay, so the Z component of this vector value is the one you're looking for. And corresponds to this eigenvalue, there's also a eigenvector which you could get, which corresponds to the normal direction, the closest normal direction to the fit plane to each of the normal of the faces. And that can be retrieved by looking at the 3x3 matrix of U, and actually the U looks like this. And the one we are looking for as vectors, the eigenvectors, corresponds to S1, S2, S3 is these. So A stands for the X direction, D stands for the Y direction, G stands for the z direction for eigenvalue S1. Since we are looking for the smallest eigenvalue, which is S3, what we want to look for is this C as an x coordinate, F as a y coordinate, and I as a z coordinate. So that is these two are the value that we want to look for, get out of these SB decompose. So let's try to get that and try to visualize it to see if it looks correct or not. Alright, so first of all, let's remove these. The value for the eigenvalue, I'm gonna call it eval. Sounds like a different method. How do I call this? This is also can be considered as the amount of energy, so I'm gonna just call it E, and that is S2, the z component of the vector S. Then vector eigenvalue, eigenvector, I'm gonna call this EV, is from U, but what we want to get is this value here, this value here, and you could get that by from the 3x3 matrix on Houdini by saying, so this value is xx, and this value is xy, this value is xz, this is yx, this is yy, this is yz, and this is zz. So what you want to get is the xz, yz, and zz component out of this U 3x3 matrix. So u dot x z, u dot yz, and u dot zz. Okay, so that's the value, and this should be the normalized value, meaning the length is equal to 1. This is the unit vector. Now let's try to check this direction first, if it really looks like the normal direction of the plane, the fit plane. Okay, for the covariance normal. So we are going to give this as an attribute, as well as the energy as well. For the energy, I'm gonna call this En. Okay, like that, and then let's try to visualize it. Now I think it's a bit hard to see with this example if the value is correct or not, so I'm gonna try with the more simple geometry like cylinder, which we could easily estimate what the normal plane, fit plane's normal direction is. I'm gonna give a little height, little bit of meshes here, and also make it triangular face like that, and connect this right here. Okay, and let's try visualizing the EV as a vector. Make it red. Okay, so it's facing upward. So is this correct or not? I'm going to make this change the resolution, and it doesn't really change the direction. Now let's consider if this seems like a correct value or not. Looking from the top view, we have a hinge-like face, a hinge-like shape for each point. So obviously these are unfoldable, meaning developable for sure. All the cylinders are like that. And if we check that shape on a sketch, looks like these. Something like that, okay? And consider we are looking at this point on the center, okay? And looking at each normal face, the face normal looks like this direction, and the plane which fits with these normal are something like this, or maybe no, sorry, that's not correct. Actually, the face that aligns, that each normal fits, is something like that. It's a bit hard to see again. If you look from the top, view, the face looks like perpendicular to this hinge, and the normal is facing this way. So you can see that the normal is on top of this plane. And the normal direction of this plane itself is actually this upward direction. So the red arrow that you're seeing right now looks correct. Okay? Makes sense? So this is what you called U here. So seems like the estimation is correct. And going back to the pig head, and let's make the lengths of each eigenvectors a little bit small. Each one is actually a best fit plane's normal direction. Okay, so and this direction is going to be used for in order to calculate the gradient, meaning the direction and the actual direction, in order to optimize the point to make it developable. All right. Now another things we want to check is the eigenvalue, which is the energy that we need to decrease in order to make it equal to 0 for the best fit. That is En. So bigger the value is, less appeal, less developable that point is. So let's also visualize that by, I don't know, maybe using color node. Ramp from attribute using En. Now let's make the 0 to white and 1 to red. So more red it is, more undevelopable. And you can see it happens where you have a high Gaussian curvature, I think. Let's also compare with the measure node, which calculates the Gaussian curvature. The curvature for each point, and see how it looks like. And it's a bit too bright, but comparing this and this one, you could see some similarities. Now Gaussian curvature has the negative value as well, so you're seeing blue and red. But if I make this red as well, you're gonna get the absolute value colored. And so compare with this one and this one, you get somehow close estimation. So more high Gaussian curvature you have, less developable. So making the Gaussian curvature close to 0 is also a goal as well. You could say that. Right. Now, enough with the checking. Now that we have got these information as the energy and the eigenvector, it's now time to calculate the actual gradient, in which direction we should move the point in order to make it less energy, less energized as the undevelopable condition. To do that, first of all, I am going to sum all the energy which belongs to each point. Right now stands as En, and each point I have this En value in 64 precision. I want to add all those values together as one value to estimate the total developable energy. So less the maximum, less the sum of these energy is, the better. Okay. So I'm gonna promote it to detail, change the name to sum En. Don't delete the original because we might want to use it. And we are looking at the energy. And as a result, we could get the total sum energy like this. Is this correct? I don't know. No, I don't think so. That is because I didn't add it all together. I have to make it sum. Yeah. So 66.2. Now the goal is to make this become close to 0. Okay, so that's the goal for the optimization, right? Now we could gather this as one pack. Now it's time to calculate the initial gradient, the direction for the actual energy for the optimization. So first thing first, where shall we start? First of all, I am going to create the empty attribute called gradient, which stores the vector value in order to define the moving direction and amount for the optimization. So attribute create call this gradient, starts from 0, make a vector value. Alright, now it's time to calculate the gradient with another vex function, and that's when you go to the appendix B1 and B3. This one, this one right here, and this one right here. Okay. All the rest is kind of optional, like something like maximal covariance is to make a bit better result, but it's a bit more high cost to calculate, so I'm gonna skip it for today. And B2 is for the combinatorial energy, so we also skipping that as well, because what we are using here is the covariance energy. Okay. But for this B1, this is general. This is going to be used for combinatorial energy and covariance energy. So first we need to calculate this one. Then we could start calculating this to estimate the gradient direction. Okay, so shall we do this? And this is going to be a lot of calculations, a lot of vector or matrix calculations, so be aware. Not that hard, but a bit confusing. So what we want to do again is the calculation for each point. Okay, for each point we want to calculate the direction in order to estimate in which direction the point should move in this step to make it developable. Now it cannot be optimized in one step. You need to have tons of steps to optimize because all the points are moving at the same time. So you need to also estimate how much you should move to that direction. So that is going to be done in the next step in order to do the linear search. What's the best step? How much you should move for each frame. Now, but for now, we just need the direction, so let's do that. Using the point wrangle again. Let's call this gradient. Calculate gradient. Now, let's go one by one. Now, first thing first, we again are going to calculate the phase-wise values, just like listed here. We have I, J, K, and so on. So we need a primitive which belongs to each point. So do the same point prims at each point. All right. Now, let's also bring up the eigenvector value, which in this case the eigenvector is used as x right here. X is the eigenvector value, which the length is equal to 1, meaning the unit vector. So let's call the eigenvector value equal to x and get that from the attribute called EB. Alright. Okay, so let's create the loop to go through the primitives. Like that. Okay. So first thing first, what we want to do is to probably calculate the area, probably. And we can calculate the area using the simple cross product function, which I'm not sure if this one is correct. This is like a cross vector between the face of the normal and the edge between fk and fj, which is creating the vector value as an output. But I think what we want as the area here is the scalar value. So instead of doing like this, what I'm gonna do is to first of all get 3-point position. Okay, one is I, one is J, and one is K. Right. So in order to do that, I'm going to first of all get the value, get the point numbers for each primitive. And in this case, the order is pretty important. The order of I, J, and K. I mean, it could either be clockwise or counterclockwise. Either way is fine, but it has to be consistent. I mean, if you took different triangles and different places, and if this one's I, this one's J, this one's K, and in this case, if this is I and this is K and this is J, in this case, this is counterclockwise, this is clockwise. So we don't want these conditions to happen. We always want to have either clockwise or either counterclockwise. So in order to get the consistent order for the vertices. Instead of using the prim points, I'm going to use instead a prim vertices, which will always get the triangular faces vertex order. So which is always become, in this case, clockwise, I think. So it's a bit dangerous to use prim points because it just mixes up the order for each face. So prim vertices at prim, like that. Now what we want to do next is to convert each vertex number into I, j, and k, and we always want to use I as the current point number, which is equal to pt num. So let's create that kind of conditions. We can't use I don't want to use I actually. Instead of using I, let's make it t, because we want to use I as this value here, ijk. So we want to preserve these ijk characters. I want to preserve it. So for int n is equal to 0 and VTS, and we can get the vertex number, and then we want to convert it into a point number by using vertex point, like that. Then what we want to do is to check if this point number is equal to pt num, and if it is equal, then we want to make this point number as I. Okay, so if pt is equal to a point number, the current point number, then we want to make the I is equal to pt. So we have to have I somewhere, probably right here, as well as j and k. Okay. So if I is equal to pt, then j is the next point, next vertex point. So VTS n plus 1, and there's a possibility that this becomes 0, so calculate the remains by, in this case, 3, because we are looking at the triangles. There's only 3 vertices. And we also need to convert this into point numbers, so vertex point 0, vertex number. And do the same for k, which is n plus 2. And then you'll get a value I, j, k stored. And you always get I as a pt number. Now this, once you find out that pt is equal to pt num, then you don't really need to go through all the other iterations for the list loop. You can just skip it using break. Alright, now that you got a 3-point numbers for this triangle I, j, k, it's time to calculate these value. Now in order to solve this, first thing first, let's get these point position at I, j, and k. So position I, you get like that. Oops. And j and k do the same thing. Oops. Like that. While I'm writing the code, if you guys have any questions, let me know. So you get ijk position for each face in this loop. Now, I think we have enough information to calculate all those stuff. Let's do that. First of all, we're going to calculate this area for each face, which is pretty simple. I mean, we could do the measure node to calculate the area for each face, but I realized that the measure node, in order to calculate the area, is pretty computationally heavy, expensive somehow. If I run this on inside a loop, the most expensive node out of all the stuff was actually this measure node somehow. I don't know why. So instead of using measure node, I'm just gonna calculate it as a vector value using the linear calculation. So to do that, what you could do in order to calculate the area, if you have a triangle like this, first you want to get the vector between A and B, B, A, V, and also the vector between A and C, V, A, C. Okay, and by calculating the cross products, you get this perpendicular vector. And actually the magnitude of this vector is equal to the area of this square. So if you divide it by 2, you get the area of this triangle. Okay, simple as that. So we're going to use that equation formula. So I'm gonna name this A, or dA. dA is equal to a cross product between the position j minus position I and position k minus position I, and divided by 2 before we're gonna get the magnitude of the vector. Then this will become the area of the triangle associated with the ijk. Alright, so that's that. Easy. Now, next, what we want to get is, let's see, what kind of value we want to get. Probably this one, a normal value here. Now if we look at it, if we check what will be the unit of this value, not the unit, but what's the type of this value. So this is the scalar, so that's that. This is the vector value, right? And this is also the vector value, the normal of the face. So you are calculating the cross product, meaning you get a vector value. And then you get the transpose of the vector. So that means you are pretty much doing the same things as this calculation here. Meaning you get 3 by 3 matrix out of this calculation. So as a result, you get a 3 by 3 matrix as this value. Alright. And for these value, which is a delta fj theta ijk, delta fk theta ijk, and so on, is looking at this. First of all, this is a cross product. So this is the vector value, and you are dividing with a scalar value, so the result is a vector value. So all of these, the type of the value is vector value. Okay, and that is, looks like dependent on the, it says theta, so looks like it's dependent on the angle. It's not you actually calculating any angle right here, but it actually based on the angle value for each I, j, k. Okay, so Consider that. Let's try to, remembering that, let's try to calculate each of these value. We could go from this one, probably, the 3 by 3 matrix value. Okay, so in order to do that, let's see what kind of information we need. First of all, we have this one, fk minus fj. We also have all sorts of directional vector value. F stands for the position at that point. So in this case, position I, position j, and position k. Maybe I can just rename it to fi, fj, fk. Right? Looks more similar. So let's calculate this one. Each of these direction first, shall we? So fk to fj to fk. Vector f jk is equal to fk minus fj. Vector f ji is equal to fi minus fj. Vector f ik is equal to fk minus fi. Right. Okay. Now let's calculate this one. That is the cross product between fjk and the normal of the primitive. Do we have the normal of the primitive? Yes, we have calculated right here, so we can get it. Oops, we need to rename this as well. fj, fi, fk, fi. Alright. Where was I? So the normal direction of the face is, how do we call this? Just n or norm? Yeah, norm is prim 0. And which primitive are we looking at? This one right here. So n at prim. So the result is matrix 3. Well, let's call this dn is equal to, first we're going to calculate this one. Cross product between the fik, fjk and norm, and calculate the outer product between this vector and the normal. So outer product between the cross product and the normal, then finally divided by area, like that. Okay, makes sense. And that is for fi. Okay, so these, we're looking at this triangle here, looking from this I, if this is the point number that we are looking at right now. And actually we want to do the same calculations for this point and this point, the j and k as well, because in order to calculate the gradient, we are going to calculate the we're going to look for each face, and we're going to calculate the gradient at each point on this triangle, but at the same time we want to calculate the gradient on the other side, the f and k as well. So in order to do that, we need to have the f and k version of this equation, which doesn't really say it here, but it actually does. You do actually need it. So let's call this dn as dni, and what we need is the dnf and dnj and dnk as well. And wait a minute, we should call this jk. Wait a minute, the subtraction looks wrong here. doesn't it? This is fk minus fj. Oh well, looks okay. Fk minus fj, but the fj shouldn't come on the right hand side for this calculation, I think. So we should make it fj minus fi. And this will be fi minus fk. We're gonna think about these theta value later. So meaning we can rename this to fij and fki. Alright. So that it's in the order either clockwise or counterclockwise for these direction. Okay. Yeah, that should be right. And then I'm going to calculate the dnj and dnk. Okay, so dnj, we can replace this fjk to the one that doesn't include in here, so that is ki. Right, and this one is fij, like that. Okay, so everything, all of these will create a 3x3 matrix, and each one will create the gradient vector value later using this equation. Okay, now next we're going to calculate this theta value. Okay, so let's name this vector d theta I, since it says I here, and maybe I'll just say ti, dti, dtj, dtk. Okay, and we're going to calculate each of them. Okay, now this one, the one that says fi theta ijk. So we're gonna start from this one, shall we? Oh well, it's using all these ones first, so we're just gonna calculate the f and k value first. So I mean the j and k. So this one and this one. So this comes later. Okay, so j, that is the cross product between the normal and the vector fij. So cross product between the norm and fi minus fj. So fi minus fj divided by the length of fi and an fj. So I guess you could just normalize this one as well, because this means you are using the normal unit vector. Okay, but let's just follow as it is. Okay. And I assume that this could also be length 2, but I'll just keep it as this for now. Right, now do the same for dtk. I'm just gonna copy these and cross normal fk minus fi and do the same here, fk minus fi lengths. And finally you are subtracting these value. So minus dtj minus dtk, like that. Okay, so that's that. Now I think you have enough information to go for the actual gradient. These are the preparation, and this is the actual equations that you want to solve in order to get the actual gradient. At any vertex I on V, this is the every vertex, let lambda be the eigenvalue of the matrix. Alpha ai is equal to with associated eigenvector x, and we're going to use this x, which we got here. Then the gradient of lambda with respect to the position fp of any vertex p is this. So this is the final gradient value, and that is the addition for each face on each point. So meaning you have multiple faces, so you could still use this loop, I think. And you are calculating the transpose of x and normal of the face, which means the dot product. Okay, so the power of 2 of dot product of these two vectors, then multiplying with the fp ijk. So since we have it says p, that means we are calculating all 3 points for each face, I think. Okay, and use it for each gradient for each point. So we gotta store which gradient used for which point. Okay, then we have 2 theta ijk multiplied, but this is a scalar value, I think. This is the angle, and this is another dot product, which is same as this one. And then we have a 3x3 matrix, and you are transposing it and multiply by x, which is equal to vector value. So as a result, you get a vector value. 3x3 matrix multiplied by vector value, you get ax plus by plus cz on the first row, and dx plus ey plus fy on the second row as one value, and gh plus hy plus iz on the third row. So as a result, you get vector value having 3 rows and 1 column. So this will become a vector value, and this is also a vector value, so the result is vector value. So this is the vector value. Alright, so what was I? It's time to calculate these. Since we are having the same dot product calculation here, let's gather that and make it as a variable. I'm gonna name this x dot n. Calculate the dot product between the x and the norm. Alright. Which will give you the projected lengths between the x and n. Not really, but okay, well, so we have this one, and since we are adding all the result on this loop, let's give a global variable. And as I said, you are going to create the... Actually, we don't really need to make it global, but we can just add it as a attribute as soon as I create this lambda, d lambda. Okay, so I'm gonna call this dl, stands for d lambda. And first of all, the left hand side calculation, which is the dot product of these x and n, which is this x dot n, and power of 2 square of x dot n multiplied by this is actually a vector value, so in Houdini we need to bring the vector value on the left hand side. So we have this value already, which is either this one, or this one, but this is fpijk. So in this case, what we're gonna use is for the I. So we are going to calculate 3 gradient, 3 lambdas, dlj, dlk. Okay, so for the I, we're going to use this one. For the theta related value, like that. So dti, d theta I, which is this one, multiplied by the dot product, the square of dot product, plus 2 multiplied by, actually we need to also bring the vector value first, so we should calculate this value first here. So fin, in this case dni, which is the 3 by 3 matrix, and x is the vector value. And since in Houdini, in order to apply a matrix or transformation matrix to a vector value, I think you need to bring the matrix on the right hand side, because in Houdini the vector is horizontal, expressed as horizontal value. That's a bit confusing because in a lot of the papers the vector is expressed as vertical value, but in Houdini it's not, so I think we're gonna do like that. Then as a result you get the vector value out of this calculation, which is these. Then you can multiply with these flow value, which is multiplied by 2, multiplied by theta, multiplied by x dot n. Do we have theta? We don't have theta here. Yep. So we need to recalculate that theta, which we have done on calc energy as well. So we're just gonna copy this one, bring it here somewhere, maybe here. We need to change the name to fj, fi, fk, fi. Alright. Right. In this case, the theta is always looking at the angle from the eye, so I think this is constant. We don't really need to calculate the angle for each points, ijk. We are always looking at this angle for this vertices, even though we change the position to calculate the force, the gradient, because it says I here. Okay, so that's that, and I think this is done, and we do the similar calculation for j and k. So we're gonna copy this, paste it right here and replace some of the variable. For example, this one, this will become dtj, this will become dtk, and this will become dtdnj, this will become dnk, and I still have some errors somewhere. Let's see where that is. Syntax error, an expected on the identifier on 48. Hmm. 48. Where's that? Right here. Okay, it's fixed. Not sure where was the problem. Okay, let's save it. So hopefully this will be the force value in order to the gradient value in order to move the point for the best position for the developability. And let's see. And what we want to do is to store this gradient into a point as a and summarize. I mean, get the mass addition of these gradient on each point, the corresponding point. In this case, this is for the I, this is for the J point, this is for the K point. So in order to add these gradient value to each point as an addition, I'm going to use a function called setPointAttriv to a gradient attribute to I with this DLI as a add option which will apply an addition for these vectors to this gradient attribute, and do the same for J and K. Okay, there's that. And if it goes all okay, you get the gradient vector attribute on each point just like that, which shows the direction and maximum force in order to make the point, in order to make the mesh developable. But if you just apply this length, this speed directly to each point, then the mesh will just collapse because these energy is only for only estimated by looking at each neighbors for each point. So if by moving each point's energy at the same time, you need to make it really slow to make everything works at the same time to get the balance, you know. So shall we visualize this gradient value first as an attribute? Gradient as a vector value. So looking at each point, seems like these are the direction in order to make the mesh developable, but we cannot really see if this is correct or not, so we have to test it out by using some solver or for each loop, feedback loop. But we could kind of see how it's gonna look like on already a developable surface like cylinder. In this case, you can see that the gradient, you no longer see the gradient arrow, and if we look at the geometry spreadsheet, the gradient is equal to 0, meaning there is no need to optimize because this is already optimized as a developable surface. So that kind of makes sense. So we could assume that this might be correct, but let's see. in order to check, we need to use this actual gradient value in order to move the point slowly to that direction and recalculate the gradient after moving the points again, and move it to that direction slowly again. So let's bring these step inside the solver to see it in the animation, shall we? So create a solver, and I'm gonna copy all these stuff, the energy calculation and the gradient calculation, to the solver like that. Okay, and then we want to make sure that at each step, oops, this should be on the last. After each calculation is done, all the attributes gonna be resetted, because we don't want to use the leftovers on the first step of this solver. So let's see what kind of attribute we have. We have a sum of the energy, which we can resolve it, I think. We have energy and energy eigenvalue and eigenvector and gradient. Actually, I think we can just keep that as it is, maybe because these are going to overwritten by the function. Maybe not the gradient. I gotta make sure that the gradient's gonna be resetted on each step. So I'm gonna create the attribute delete to reset the gradient, just in case. Okay. Other than that, I think it's fine. Alright. So, what we want to do is to use the gradient to move the point to that direction. So, I'm gonna use the simple point wrangle to do that. Update the point attribute with the gradient on each point. As you can see, if you just use the gradient as it is, the mesh just explodes because the speed is too fast, obviously. So we're gonna make sure the speed is small enough so that each gradient won't you get the best balance in order to optimize. And currently we don't know what's the best value for this time step or speed. So let's just try out with a random value like 0.0001 for now, and let's see what will be the result. If I play it now, looks like the value did a nice job. Looks like it did seem to create some kind of a developable surface that we were looking for. And if we cusp the edges with some angles, like using the normal for vertices, make the angle like 15 degrees, you can actually see the edge cusp or edge standing out, and looks like we are getting some kind of a developable surface out of this. So for this mesh, maybe the speed was okay, 0.0001. Though, the problem is, I think if we increase the speed like 0.006, because more speed you have, the faster you get the result. But if you make it too fast, the problem is you get the noisy result, or sometimes it's wiggles because it's moving too fast. It's going back and forth. If you make it more faster and faster, now you start to get the unwanted result. That's not really what we want. So we're gonna have to make it as fast as possible, but not too fast to make the stable optimization. So in this case, maybe 0.0002 might be a good number. Maybe, but still, it's still wiggling, meaning it cannot find the best result. What we want to have is to stop these wiggles and have the fastest result as much as possible. So the next step is to estimate what is the best time step for each iteration. In each iteration, the time step will vary. Sometimes it could be better for 0.1 for the larger mesh, maybe on when the mesh becomes close to the developable surface, then the time step might become really slow. So we gotta estimate this value, and that is the part where you do the linear search for the optimization, and that is explained in the paper where it says Numerical Optimization here, and it explains you could use LBFGS, one of the type of linear search. This could be the best result. It says by using this one you could get the best result. Other than that, there is also another type like Almijo, Wolf, line search, and so on. There are a bunch of line search algorithm. Although I haven't looked into these stuff myself, so what I'm going to implement today as a numerical optimization is the really dirty implementation of the linear search. So it's not really based on LPFGS or Almijo Wolf. It's just my own implementation, which obviously is not perfect at all, but at least it could kind of find some sort of time step. So, and probably you could just edit it or modify it to make it similar to LBFGS or Almijo Wolf line search later by yourself. So I'll left that to you guys. Okay, I'll just show you the very basic linear search method using the Houdini way, using Houdini node. Probably it's better to do all in code, but I'm just going to use a bunch of nodes to create this kind of a line search to make myself understandable, right? And there's another like optimization tips explained here, like fixing the mesh by flipping the edges like these to meet the Dirac conditions, or collapse the edges like these one. But I'm also going to skip that part as well, okay? Because these topics also takes a bit of time to implement in Houdini, okay? But it's also, I think these are also important in terms of the optimization. So I might gonna do this in other video as a separate topic, probably. Okay, so for the numerical optimization, the way that I tackled this problem, I'm gonna explain in Sketch. Okay, so the way I have tackled to this problem, I don't know if I can sketch it correctly, but first of all, you get a geometry and you get the direction as a gradient, right? But what you don't know is how much amount you want to move in the specific frame. So what I'm gonna do is to repeatedly move this point to this direction with different distance and find the best distance for each step. Starting from a really big distance like t time step t equal to maybe 1.0, which is pretty fast obviously, and by moving the point to this direction, you get some kind of a new shape. And out of this new shape, what I'm going to do is to recalculate the energy, the new energy. I'm going to call this new E. Okay, and previously you have already calculated the energy, and I'm going to call this old energy. Okay, and what I'm going to do is to compare these two energy together. What I mean by old energy and new energy is the sum of all the energy on each point. Okay, so in Houdini I have created the attribute like sum en. So this is the attribute that I'm talking about. So if the on is larger than the new n, then that means you are successfully make this energy smaller. Okay, what you want to make as a final result is, if we have the graph like this, and this is the total time step, and this is the energy, and starting from this energy, and what you want to have is the energy equal to 0. So you want to move the energy to the this direction, the downward direction. It could be like this, or it could be like this, any other way, but you don't want to go to this direction, upward. That means you are increasing the energy. But instead you want to decrease the energy somehow. So this is the result you want to get. Comparison between the old energy and the new energy, right? But if you make the time step too big to move the point too fast, the chances that you get this condition. The new energy is bigger than the old energy. That is not the condition we want. So in order to avoid that, once we get this condition, we are going to make this time step smaller. Let's say multiply by 0.5 and make it 0.5 in the next step. And using the new time step, we're going to recalculate or re-estimate the new energy, like moving the point to this direction, create the new shape, then recalculate the new energy and check the condition again. And if the condition is still too big, the new energy is still big, then we're going to multiply this time step by 0.5 again and do until this new energy becomes smaller than the old energy. Once it becomes smaller, then that's the time step we want to use, largest as possible. Okay, could be like 2.2, 0.1, something like that. And using that time step, we're going to move the points, and the new energy will be smaller than the old energy. Okay, and that is going to be calculated in one iteration of the solver. Okay, once you move the points with the new energy, which is lower than the old energy, then you are recalculating with the new mesh, which will become the new energy will become old energy, the previous new energy. Then do the same step again on the next solver iterations. And you can reset the time step to 1 again on the next iterations, but that takes a bit of too much time. So we could estimate that the next time step for the next iteration of the solver could be close to what we have find out on the previous iterations. So, but we also want to make the time step as big as possible, as large as possible. So what I'm gonna do is to multiply this 0.2, which was declared in the previous iterations, by 2, so that it starts to search for the time step from 0.4. Okay, So starting from point 4, again you're gonna do the same step, move in this direction, move into the gradient direction with a time step of 0.4 and check if the old energy is bigger than the new energy, and if so, 0.4 is good. If not, you're gonna multiply by 0.5 again to get the new the new time step. Now this multiplication by 0.5 or multiplication by 0.2 on the next iterations is just my guess, so I don't think this is the best way to do the linear search at all. This is not really, I don't think this is a good optimization at all, honestly, but it'll do some kind of job. I mean, at least it won't explode your mesh, so still works. And I believe by modifying this optimization with the algorithm explained in other papers like the BFGS, LBFGS, then you could make it more precise, maybe a better time step. Okay, but for now, let's just make it essential or basic, right? So keep that in mind. Let's find out the best time step, shall we? All right, and another things that I want to mention is right now 0.001 seems to work well with this mesh. That's good. But once you change the resolutions of the mesh, like changing the area of each mesh and so on, the best time step will change. If I change this to 0.2, then maybe the time step is a bit too slow. If I make it high res like this, maybe the time step was too fast. Okay, so that's also the reason you need to look for the best time step for the best optimization. Okay, at least in order to avoid exploding. Alright, that's that, and let's see how we do that. And that part is, I think it's pretty important. Right, so going back to the solver, and I'm gonna gather these, I'm gonna name this energy calculation, gradient calculation. Okay, so as I said, we need to check a lot of time step inside a single iteration of the solver. So what I'm gonna do is to use the for loop several times until it finds the best value. Okay, and I think it's better you use the while loop in Vex rather than using for loop, but I think it's easier to see with these using for loops, so I'm just gonna go this way. And to make sure that you have enough iterations, I'm gonna make this iterations big enough, like 1,000 or something, because eventually it's going to stop at some point. But for testing, I'm gonna limit it to 100 for now, and later on I'm gonna increase this value. Let's make a feedback loop. Do we need it to make a feedback loop? Yes. Yep. So fetch feedback loop. All right. Then I'm going to connect this right here. And I want to test the result with a bit more rough geometry, so let's make it 0.1 and something like this. Okay, so let's see. first thing first, I would like to have an attribute to store the time step as a global attribute. So we can go outside of solver, start creating the attribute that we might going to use and update it. I'm going to use the attribute create name this t as a time step for detail float starting from 1. I guess 1 is pretty fast, so eventually it's going to be smaller at some point. Probably. I don't know, maybe it might be okay to start with a really big number, but I'll go with 1 because what I'm gonna do in order to decrease this time step is just a simple multiplication. So maybe if I use logarithm or something like that, maybe this could be really big, but since it's just a linear multiplication here, so I'm just gonna go with a small enough number like 1 as a scale speed. Okay. Go inside, and first thing first, what we want to do is inside a for loop we would like to test this time step that we have in the detail attribute. Didn't have it. Where did it go? Okay, we have to connect this here. Okay. So we have this t as a detail attribute here, and we want to test if this t is okay to go or not. In order to check that, I'm just gonna make the simple assumptions just by moving each point to that direction with this speed and recalculate the energy using the same function that I have here. So I'm gonna use the point wrangle to move the point to that direction with the gradient, just like I did previously. Multiply by t, retrieve from the detail, like that. Okay, obviously this is too fast, but let's check what the energy is. So I am going to copy these. First calculate the normal of the face and calculate the energy at each point, and get the sum of that energy. And I think it's a good idea to change the name to something else, so let's name this new sum n. Okay. And then let's just go with single iterations for now. See what's the result. If we look at the geometry spreadsheet at detail, as you can see, sum n is the old sum of energy, and the new sum n is the new sum of the energy, and obviously the new sum energy is bigger, which is not optimal, which is not good. What we want to have is the one that's smaller than the old sum energy in order to optimize. Okay, so obviously the t value is too fast, we want to make it smaller. So how do we do that? We're going to check this new sum and the old sum inside a loop, and if it's smaller than, then we're going to update the t value somehow. So let's do that by creating the conditional using maybe a detail attribute. Okay, let's make the attribute wrangle and make it as a detail, and the old energy is f at en sum, or sum en, was it? What's the name? Sum en, yeah. And the new energy is f at new sum n. Okay. So, and the current t value is f at t. So if new sum, new energy is bigger than the old energy, that's not good. So we're going to update the t value to the t multiplied by 0.5. Maybe this is decreasing too fast, but let's see if this is okay or not. Right, and else else that means you have found out the good value for the t, at the largest as possible t value, which makes the energy smaller. So that means you want to stop the loop. So I can create some attribute to indicate that we need to stop the loop at this point. I'm gonna create the integer value for the detail as stop to stop the calculation. So that means we need to reset the stop somehow, somewhere, maybe outside the loop, somewhere around here. So I can just say attribute delete before getting into the loop for the detail to delete the stop attribute, just in case. Alright, now we could create a null node somewhere around here to retrieve the stop conditions. To check the stop condition, I'm gonna create a null node here and check if the detail attribute of this stop node is equal to 1 or not. If it's equal to 1, then we're going to exit this loop. Stop. Okay. And increase the loop here to 10. And after we have updated the t, we could see that the t is decreasing like that at each step. If we make the step to 2, this will be like 0.25, but nothing seems to make this optimized. That is because we are like adding the point position over and over again. We have to somehow reset the position in order to test out the best time step at some point. So we're going to reset the position to the original position. This is the original position at the end of each loop. Okay, so to do that, I'm going to create the rest position node before going into the loop to remember the original positions, and each time we recalculate the energy and recalculate the t value, I'm going to reset the position, reset the point position, which has been used to recalculate the energy to the original position somewhere here. So I'm going to use the point wrangle, reset position, just make the position to the rest position to reset it. Okay, like that. By doing this, at some point you should see this stop becomes 1 and you get the best t value at some point, hopefully. Let's increase this to 100 and see where it stops, and it says the feedback loop stops at 14, so that's the end of the loop. And that's when you have found the best t value, which it says 0.0002444141. So seems like this value is the largest possible t value for this condition in order to make the new sum energy smaller. And if you compare these two, yes, the new value is actually a bit smaller. So looks like this time step is a good one to go. Okay, now that we have this value, we could move this pig head to that direction with this t value using another point wrangle. And getting the updated t value from the detail. Move the point to the gradient, multiply by t. And you get some result. That should be the that should be equivalent to what you have found on the last energy calculation. Alright, so that's pretty much it. And after that, you could reset some of the attribute which is no longer needed for the next iterations, especially the new energy stuff. After this, you don't really need the new sum energy anymore, so actually we could keep that as information. So, but before getting into the global, maybe we wanna remove that for each time step or each loop. We might want to remove that, probably. I don't know. Let's see. Maybe not. Maybe not. We could keep that. But we do need to reset this t a little bit. I mean, as I said, if we keep the t as it is for the next step, then the t will only go smaller, and making the time step t smaller means the optimization goes slower and slower and slower. But what we want is to make the optimization as fast as possible. So we do want to see if there's any chance to increase the time step at some point. So to have that kind of chance, we want to increase the time step a little bit more on the next iteration of this full solver somewhere to see if the new increased time step could be used in the next iterations. It might not be useful, but could be useful. So in order to do that, I'm going to update the time step t just like that. And before going into the testing or the linear search, just to make sure you have seen the chances that t could increase. Now this part, if I wrote it like 2, but I don't think 2 is the optimized value for the multiplication, so maybe this could be, there are some algorithm to define this value as well, but for now, let's just make it simple enough. Okay, so that's that, and I think that will do the job. Let's cover this with the group network and name this line search. I'm gonna name this dirty line search. Okay, and let's see. We're going to look at the detail attribute to see the changes. Okay, we are missing some part thing here. Okay, somehow we are missing the energy from the detail. I don't know why. Are we missing the output? We do have an output. I don't know. Let me just play it and see how it goes. If I play it, okay, start to see some values. And you are getting the result, the good result, and you can see that the time step value t is changing through time. Like previously it was like 0.0002, but when it gets more optimized, the value becomes smaller and smaller. And also you want to check the energy as well, how energy changes. If you look at the sum energy here, new sum energy and sum energy here, the new sum energy is the current energy actually. And if you look at it, it's getting smaller and smaller, going into 0. Okay, and when it becomes 0, then all the mesh becomes totally developable. So that's the goal, but it probably takes a lot of time to make it going into 0. So you gotta kind of get the balance to see at some point this value stops, meaning it's going to converge to some value. So maybe that's the limitation for this mesh, to make it developable. Or maybe if you improve the line search, maybe you could make it close to 0 more and more. But for now, since the speed is going slower and slower, the result you get is going to become the 0 value that we want to have is gonna be slower to get. So, but at least you don't really see the mesh exploding because we are controlling the time step. Alright, good result, nice result. And I think that's pretty much it in terms of the basic implementation of this geometry, and I have forgotten that make this bigger, like 1000, just to make sure we have it searched enough. And I guess we could also change these part. Maybe if I'm multiplying 0.5 is making the speed too slow, maybe I can check by multiplying by a little bit bigger value than 0.5. That will make the speed faster, but the cost of calculation might get bigger because it makes a lot of iterations to find out the best time step. If you look at it, you see that you need 32 steps to find the best result when you multiply 0.75. If you make it 0.5, you only need 15, so on. But if you make it too slow, I mean, you don't need a lot of feedback, but the speed gets too slow, too fast. So that's not really what you want. So you gotta find the best balance in terms of the CPU, the calculation cost, and the speed of the optimization. And I think the algorithm for these will solve that problem. Yeah, to find out the best constant value for these. Alright, but that's my way. This is just a dirty way to implement. At least this works. If I make it 0.75, the result becomes a bit faster. So in this case, maybe 0.75. It's a good idea. Alright. So, yeah, that's it. The result looks promising, and there are a lot of stuff you could still implement out of this paper. I just have explained the essential part of the paper in order to create the developable surface. As you can see, there are like mesh cleansing like these, or you could also consider the conditions like these. Like the one that I have implemented will get the result like these, but if you want to get the clean result like these, you need to change the energy calculations a bit more using this maximum variance somewhere explained, maybe somewhere on here. And if you also want to so if you want to solve these, you need to additionally add some conditions to the energy and so on. For example, these conditions as well. If you want to avoid this pointy conditions or flat condition like this, which you saw on rubber toy head, you need to add another conditions, which is pretty much explained in the appendix, so you could check that somewhere like here, somewhere like here. These are all total gem to look at for discrete geometrical operations, but for this live stream I'm just go with this essential part, which is pretty much what I needed for myself for the workshop that I'm going to do later. Okay, and that's what I wanted to share today. Okay, well, that's pretty much it. Let me know how you think about it. Hopefully you find it somehow interesting. Maybe that was too much of a implementation of mathematics, but I found this paper really interesting for sure, promising for a lot of other usage, and the way to read the papers as well, way to calculate the energy, way to optimize using some basic linear searching as well. So I hope you find somehow interesting as well, like I did. If you have any comment or feedback, let me know. I would love to hear that. Now let me check with other kind of resolutions, make it really high res, like that. See if it's going to still work. So you have really high energy here, but you are decreasing energy for sure. You can check that as a number here, and as a result you are also seeing the developability here. So that's good. That is good. Now in the paper where it explains how you can create the high-res developability surface, it says you should start from a really low-res geometry, then over time at some point you should subdivide the mesh to have more triangles to make it high-res and to calculate the developability as fast as possible. So if I want to try that, start with the really low res geometry, like 0.1 or 0.2. Maybe this is too low res. I mean, at least you should be able to see the overall shape that we want to have. So 0.15. How's this? How does it look like? Okay, so this might be good. So let's see at what frame this will converge. Well, somewhere around 500. Maybe that's taking too much time. I'm going to increase the substep a little bit, like 10. That might make the calculation slow, but let's see. Oh, it's still fast. Okay. So let's say we want to remesh this at, well, there is a condition that we don't really want, which is explained in the paper how to avoid it, but we didn't do that today. Let's just ignore that. Let's say we want to remesh it on 150 frames and go to the next resolution. Going inside of solver, let's create the switch node. Switch node. Only if the frame is the multiplication of 150, meaning calculate the remains with 150, and if it's equal to 0, then remesh, do the remeshing. And we don't want to make it smoothen out, so we want to use the subdivide node which doesn't smooth out, which is bilinear. Okay, you can see that the edge cusp is still there, and it is creating squares. So we don't really need this. We don't really want the squares, so we need to make it triangles. But looking at this, this might be too much of a triangles to add for one subdivision. So instead of using these, maybe I'll just implement the mesh by myself. Using the subdiv loop, this is soften the edge, so that's not ideal. Yeah. So instead of doing that, or this has the override crease weight attribute. Okay, so this is good. Crease weight to 10, which will keep the edge cusp. So that will do the job, I guess. Okay. So only when the frame is the multiplication of 150, we are going to subdivide once. Now there's funny condition happens here, but let's say I'm okay with it. Okay, so let's try, see how it goes. Play, and once it becomes frame 150, this will subdivide once. Okay, now it looks, oops, whoa. How come it becomes really high res? Maybe I'm doing something wrong here. Wow, that was scary. Where did I do wrong? Okay, well, let me test this with when the frame is equal to 10. Huh. I'm gonna make it really slow. Let's reset the simulations. 3, 4, 5, 6, 7, 8, 9, 10. What's this loop coming from? Oop, nope. This is obviously wrong. What is this thing? What did I do wrong here? There is only remesh here, right? Right. And what's the deal with... Funny. So this is... and this is equal to 10. This will become... this will be subdivided. Wait a minute. Okay, maybe that's... it's because I'm using sub-step here. Yeah, probably. That's the reason. Okay, forget it. Forget about using the sub-step. And make it like this. And instead of making 150, I'm gonna make it like 300. Okay. And let's check the detail attribute to check how the energy will change over time. Oops. So once it becomes 300 frames, let me see how it differs. So from 298 to 300, seems like the sum drastically get decreased. I guess that is because the t was big enough to move, so I guess I do need to think about how to increase the t value other than the one that I have implemented. Although looking good, starting to get the more high-res surface, and once it becomes to 600, you should see a bit more detailed and low energy. Nice, nice, really nice. And let's also color the surface with the normal normal color, so that you can see the differences, the normal differences between the surfaces or vertices. The different color indicates the different surface direction, and you could clearly see the change between this surface and this surface, pretty much explaining where the edge is in order to create the cut for an unfolded surface. The paper also explains how you could define the unfolding edge and how you could unfold it somewhere around here. But I am not going to do that as well. Maybe I'm gonna leave that up to you as well. I guess there are many ways to do that. But at least you'll be able to get the edge information still. And I need to do that for myself as well. I mean, I haven't tried it out yet. If I found out the method interesting, then I'm gonna share that as well at some time. But at least for now, I have just implemented this essential part and pretty satisfied for myself. Okay, that's it. Thank you very much. Thank you, really. Thank you for the comment. Thank you for watching this time. That's pretty much it for tonight. You could use the same method for all the other geometries. You could try to check that with the sphere as well. could be interesting. This might be too low res. Interesting. Doesn't really look like a sphere anymore. But this is going how it's been optimized for sphere mesh. I mean, there are also a condition explained in the paper how to resolve these, like 3 points positions, or these as well, how to resolve these conditions as well, explained in the paper, so maybe you want to look into that as well. But overall, looks good. Okay. That's okay. Okay. Serial. Thank you about the comment. That's it for tonight, I think. I'm going to, as always, I'm going to upload the files to the GitHub so that anybody can download it for free. I'm going to paste the link of this project to the video description page of this YouTube. Also, I'm going to upload the files, the same file, to the Patreon page. So if you could support me on a Patreon, that would also be awesome. But anyway, you could just download it for free from anywhere. Okay, so that's it. Thank you. And I think that was a lot of mathematical stuff for tonight. Maybe not so interesting visual wise, so some of you might find it really boring, but I hope some of you find it interesting. At least I did. Okay. I haven't figured out what the topic will be for the next week, but probably it's gonna be a bit more visual oriented, more easy stuff, more faster stuff than this one for sure. Okay. Thanks for being patient. I'm going to organize this a little bit and just finish the stream. And as soon as I finish the live stream, I'm going to upload the file. I don't think I need these. I'm going to delete it. Okay. I'm going to keep this. Keep that. Developable surface optimization. This is the visualization. This is the initial geometry. This time we didn't have any parameter to modify, so I'm not going to create any global parameters for this one. I'm just gonna leave these as it is. Maybe I could have a parameter for this frame. Probably. Yeah. What's this? This is just for testing. I'll keep it. Okay. Right. Let me just create a null node. Name the controller. Subdivide frame. I could have another parameter like how much you want to increase the t time step t for each iterations. Increment is not the right word, I guess, because you're multiplying it, you're not adding it. I don't know. Oh well, just gonna go with this. And also time step. How what's the word to make the value decreased? I don't know. Let me check the word. Attenuation. Really? Oh. I don't know. Okay. Oh no. Maybe dumping is the right word. Okay. So the increment should be more than 1. So something like that. Replace this with the time step, no, the frame. Oops. Copy this value and this one here. Right. Lastly, this one here. Time dumping, time step dumping. There you go. Okay, everything parameterized, which I could. And I'm going to check if it still works, and yes, I am going. Okay, that's it. That's it. That's it. So, thank you very much for watching. Okay, I got a comment from Serial. I missed the beginning. I'll watch later for sure. Thanks. Is it like CAD feature to unfold surface? Yeah, there is a feature in CAD software like Rhinoceros to unfold the geometry, for sure. You could probably do that on Houdini by using I don't know what's the best way to use them. Since it's assured that it's developable, maybe you could use KineFX, but I'm not sure. Maybe using or UV mapping could also work, probably, by preserving the area of each triangles. Okay, probably. Well, I have to test it myself, and I haven't looked at the paper where it is explaining the unfolding part, so okay, that's it. Nice. Okay, let me just take a screenshot and I will finish this. As the stays achievement. Alright. Okay, so thank you very much for joining. Good night, everybody, and hopefully see you next week with some different topic. And for sure, the next topic will be much easier one. Okay. I have a comment from Goody F. Can I ask something not related? How you manage Windows software like Unreal on Linux? Is it sufficient to use mine for them? I don't know. I haven't used Unreal in Linux. This is Macintosh that I'm using right now. Most of the time I only use Mac or Windows. Yeah. For Unreal I'm using Windows. So I'm not sure how you could manage running on Linux. Not sure. Good night.